I want to talk to you about high-dimensional classification, um, of course, with neural networks. And I want to talk about three different parts that influence how easy or hard, complicated learning is. And these are decision boundaries, how they look like, how complex they are, if there's noise, if there's no noise in the classification problem, and if there's a margin. Um, and basically, as a motivation, and I hope I can somehow switch slides here, I have this kind of famous picture from Berlin. You know, if you look in the from space down to Berlin at night, you can see that there used to be a divide into East and West Berlin, basically also East Germany around it. And you can see it by looking at the color of the lights. Um, and so now I could say, well, maybe this is a classification problem. I have lots of samples. These are my lights. Usually these are the street lights. And I want to figure out where is, let's say in this case, West Berlin. And a couple of very interesting things. So in the center, right through Berlin, there's where the wall separated East and West Berlin. There's a pretty sharp boundary between the two things. That's a sharp decision boundary. There are some lights that are in some sense not correct. They are essentially noise. So in the West, you see some lights that are of this more reddish color. And you see also in the East, you see some white lights. So they could be wrong. We could consider them as data points with wrong labels. And for me, quite interesting is that there are also parts which are completely black. And so there's no light there. And one can interpret this in such a way that there is just not a sharp transition between the two classes. I mean, of course, in practice, of course, there is. There used to be a border somewhere, but there's quite often there's just a forest there. And these things, where there's a forest, we could say there's a large margin between the two classes, East and West Berlin in this case, because there's essentially no mass of the distribution there of lights. And these are the three concepts, yeah. So the decision boundary that really separates, which is essentially the border, then the noise, which are the wrongly labeled observations, and then there's also margin, which in some cases separates the two classes quite a lot. Okay, we can do this a little bit more mathematically. In this talk, I want to have observations, and they are called xi, yi, and these are distributed like a distribution. So we usually have m of them. So there's a small m, this is the number of samples that I have, and the labels yi, these are always binary, so it's always 0 or 1. You could do it with -1, 1, of course, as well, or with East Berlin, West Berlin. But in my case, 0, 1 is the easiest thing. This choice will later get me into some trouble, but for now, it makes sense. And then we have a prediction rule, or that's what we want, which is we want to find, let's say, another distribution, another random variable, y hat. And it should be so that this r, this curly r, which is going to be the risk of this y hat, that, I mean, I define it here, that's the probability of misclassifying, so that the y hat does not agree with y, the true basically distribution of the labels, that this is small. Now, this is what we want. And in this binary classification problem, there is actually a perfect answer for a good prediction rule. It doesn't have to be the only one, but it is a good one. So it's not a good one, it's the best one. So you can just choose y hat as this characteristic function of a set G star. And then this G star is given as all the x where the conditional probability, so the probability of observing the label 1, given the position x, where this is larger or equal than 1/2. And this is optimal. Yeah, you cannot find a better one, but you can maybe find lots of other ones that are more or less the same. Okay, but if we look at this like visually, we're basically looking for a segmentation of our domain into two regions. One is G star, one is the complement of G star. Okay, so what makes this problem hard or not hard? And there are the three things that I already mentioned. And basically these are I mean, this is classical theory. These are you have the set G star, and it could be a complex set, and we'll talk a little bit about what that means later. But basically, the complexity of this G star is um, one of the parameters that affects this. Then you may have noise, as I said before, and you may have a large margin. We have here three examples. These are classical data sets. The iris data set on the leftmost panel and in the center. Basically, I look at it from two different angles. And in the leftmost thing, the decision boundary, I mean, it doesn't actually exist because this is just finite data set, but I just drew something. It looks reasonably non-complex. Yeah, it's simple curve, I would say. In the center, it looks much more complicated, I would say, especially since the region is suddenly not connected anymore. But you could also say, okay, in the center, we could also treat this one point that is not lying in the same region as all the other purple points. We could treat this as noise. That would also make the thing in the center harder. And if you were to try and classify these two things, you're writing a classifier, I don't know, whatever you want to use. Basically, if you use, I don't know, kernel regression or something, or some kind of kernel classifier, then you would find that the leftmost panel, if you look at the problem from that perspective, it's much easier to find a good solution than in the center. And then the right, we have MNIST, a classical problem separating zeros and ones. So MNIST is, of course, 0 to 9. And here we only look at classification 0 and 1. Also we take some two-dimensional embedding, and then we see, okay, these classes are quite well separated. So there's actually a large margin there. And in MNIST, this is usually the case. Yeah, so lots of these classes are very well separated from one another. Okay, we can do this a bit more mathematical, a bit more precise. So we need to give some kind of notions of some quantitative notions to all of these concepts. And we have the following three. So there's this complexity condition. And basically what I'm saying is, let's assume I have some kind of reservoir or a potential set of sets that I allow myself to look at. And I call this G star. So all my classification sets are from this, not G star, sorry, calligraphic G. If you can see my cursor, which I don't know if you can, but if you can, then I'm currently showing it. You can. Okay, very good. So this curly G is a potential class set of all potential class regions. And then I would say this is a complex set if it has a large entropy. Now here, this refers to the so-called bracketing entropy, but I don't want to introduce this. You can also think of just entropy. So basically, it's a large set of sets. Now, if I have a subnet, an epsilon subnet, or in this case, it would be better to have a delta subnet of it, this thing describes the size of this. I will introduce entropy again later. So at the moment, it's not so important. This is just a notion of the complexity of this set of sets. And basically, I condense everything into this one number, R. So if this entropy scales like delta to the minus R, yeah, delta is this parameter of the entropy, basically the size of the balls that I need to cover this set. If it scales like delta to the minus R, then R describes the complexity. And so a large R would mean that this is a very complex class, and a small r would mean that it's maybe a simple class. By the way, since I had to do some trickery at the beginning and move everything Zoom related out of my window, I cannot see if someone raises their hand or something. So please just interrupt me at any point. We also have this noise condition. It's similar. So basically we say, we base everything on this conditional probability here, this eta. So eta of x is basically just the probability of observing label 1 given x. And there's a very special, I mean, if this eta of x is equal to 1/2, then you have the probability of observing both labels with the same probability. Wait, I didn't say that right. Then observing both labels has the same probability. And that's a very noisy situation, right? That means there's basically no information left in this observation. It's just both labels. So this should not happen that often. And this is really what this noise condition captures. So if you're close to this 1/2 threshold, so the mass of this happening shouldn't be too large. So basically all the every observation in your domain, let's say this is modeled by this random variable x, that eta of x is close to 1/2, basically as close as t, a parameter t, should be less or equal than some t to the power q. So if q is very large, then this is a very small probability. So large q means small noise in our case. Small q means potentially large noise. And then we have as the last thing, this margin condition. It's a little bit similar to the noise condition. It's just more, it has more of a spatial component. Basically, now I'm saying there is a decision boundary of my problem, and I'm just saying this decision boundary is exactly where this eta of x that we've already seen is equal to 1/2. Or basically, because otherwise the definition is a bit messy, I'm just saying this is the boundary of the set where eta of x is less or equal than 1/2. Yeah, so this is my decision boundary. If you cross it, you will change labels. And I just don't want too much probability mass to be close to that boundary. That would be good for margin. And I describe it like here. The probability of having something that's close to this decision boundary, as close as epsilon, that should go down as epsilon to the gamma. So if I have a large gamma, that means I have a large margin. Okay, so now I have these three components, and with this, I can just describe every classification problem. Basically, if you do the following trick, then Mammon and Tsiberkov have already shown us what will happen, so basically how well I can learn something. I do empirical risk minimization, but what they do is they do it in a slightly not so nice way yet, because they don't do empirical risk minimization over a nice set like neural networks, but they look at epsilon nets. So this is just a subset of a set of sets. Yeah. Basically, you take a subset of this G curly G that we had before. Let's call this n epsilon, or yeah. And then if you have a sample, xi, yi, so labeled sample, then you can choose this gm as your empirical risk minimizer of this following expression here. So here you're minimizing the 0, 1 loss. So everything that was not correctly classified by your set, and you sum it all up, divided by m. So you take the best classifier in your epsilon net. Now, if you do the following, if you have some m and n, so that's your number of samples, and epsilon is this m to the minus 1 plus r. So r, remember, is the complexity condition. Then you can describe the error that you're making compared to the best thing that you could do, which is this G star, with the expression given in this theorem. Okay, the expression is not so nice, but you can just let Q kind of go to infinity, yeah, to think about this. So basically no noise. Then this will go to 1. Yeah, basically this will go to 1 divided by 2 plus r minus 1. So 1 divided by 1 plus r. And that's quite nice because that means if your R is really small, so you have not a complex set, complex decision boundary, you can have a rate that's m to the minus 1. And m to the minus 1 is a very fast, is the so-called fast rate in learning, and is better than what you usually have, which usually is you have m to the minus 1/2, right? And so, but if R is pretty large, then of course you can have a really slow, really bad rate. Now, this is very nice. The only problem is that no one can do this. Yeah, but you cannot find the argmin over a set of epsilon nets. You could, but then you have to just really try every element, and that's just not so nice. We want to do some learning with gradients, basically, because that's usually faster. And the idea is to do it then with neural nets. And so here's just my notation for deep learning. So deep learning is for me just empirical risk minimization over neural networks in this case. So I don't care about anything that has to do with optimization. And a neural network will be a map, and it will be a map from RD. D is always my input to NL, which is the output. And I'm saying I have, yeah, D as input dimension, L as the number of layers. Rho is an activation function, but in this talk, I think, yeah, I'm going to say it's always ReLU. I have the number of neurons, which are N1 to NL, which just describe the width in each layer. And then there are affine transforms, which I call TL. And these things make up the neural net in the following way. So my phi is just, I compose lots of affine transforms with coordinate-wise ReLU, like here. Yeah, so this is then the definition. Okay. I now need to make a little bit more precise this regularity condition, because at the beginning it was only via some kind of bracketing entropy and stuff, but this is not the world that we usually live in. I want to describe my decision boundary through some kind of more classical ways. And one thing that is quite natural to mathematicians is to say, okay, let's say this has a given smoothness. So I could look at the following set of functions. Now, this is written slightly more general than it would have to be for classification, but you'll see why in a second. So I can look at functions of this form, f1 plus a characteristic function of b, and then f2. So in the classification sense, setting f1 could be 0, f2 could be equal to 1, right? And now I want my f1 and f2 to be sufficiently smooth, and I want the boundary of b, the decision boundary, I want this also to be a smooth function. So here I'm just assuming that is locally k times continuously differentiable. Okay, it's an assumption. But this could be a nice set of functions as classifiers. And there we proved already quite some time ago that you can approximate these really well with neural nets, and then we'll talk about learning afterwards. So I can choose a dimension D, and I can choose a smoothness K. I can take a set B, which is in this cube. I choose my function f as f1 plus characteristic function of b f2. f1, f2 are both ck as before, and the boundary is also ck. Then I can always find, for every m, I can always find a neural network phi, and it only has m weights. So the weights are just the entries of these affine linear transforms. I have L layers, and the whole thing works such that the error of f minus phi in the L2 norm, that scales as m to the minus k over 2 d minus 1. And interestingly, we can also choose the number of layers to be bounded. Yeah, so it's k divided by d. And to me, this is a nice result, because, I mean, the functions that we're learning here are not smooth. They have a jump along a smooth curve. But in principle, this rate here, I mean, it's not as good as if you had just smooth functions, then it would be k over d. But it is, I mean, it gets faster with more smoother boundary curves, which is nice. And it is not the same as like what you would get if you would just have a discontinuous function. It's quite instructive, quite intuitive to some degree, because you have this k over d here. So if you have a smooth function, you have a little bit deeper layers, more layers, but you also get a faster rate, which is nice. It's slightly different than a similar construction by Jarodsky, which, I mean, that one is for approximating smooth functions, not for discontinuous functions. But Jarodsky's construction requires the neural networks to get deeper with approximation accuracy. So this one doesn't need this. Okay, so the learning result, unfortunately, or not really unfortunately, fortunately, I would say, we didn't have to prove, because someone else did it for us. So there's these very nice results by Kimono and Kim, and also by Maitsumi and Fukumitsu. And they're doing the following. So let's say you have a classifier f star. You have, I don't know what this n, I think this should be m. Sorry, this should be an M. So all the N's here are M's. So you have an empirical risk minimizer, but they don't do it for the L2 loss. They do it for the hinge loss. But I think the argument also works for L2. But I'm just going to write it with the hinge. So they're minimizing the hinge loss of this ground truth classifier of some kind of classifier, which is defined like this here. Yeah, this is where I'm getting in trouble with the choice of labels 0, 1, because hinge loss requires the labels to be -1, 1. So there's some kind of mapping going on in here, which is always shown with this tilde, you know? So this tilde basically maps 0, 1 to -1, 1. So that's why you always have this tilde appear here, because otherwise I couldn't define a hinge loss. But they're minimizing this risk. And if you do everything right, you can then show the following result. So in the worst case, all f star with this smooth decision boundary, the error decays as given here. So you have m to the minus, and then it's a slightly complicated expression, k multiplied by q plus 1, that's the noise condition, divided by q, k, q plus 2, and then d minus 1, and so on and so forth. Again, it might be more interesting, or not more interesting, but it might be sensible to think about the case where q goes to infinity. Then you can basically get rid of all the terms where q is involved, and you have something like k divided by k plus d minus 1. That's the learning rate that they get. So you can even improve this a little bit if you have margin. And well, actually, I just said a little bit, but I think you can improve this tremendously if you have margin, because now you can have the same setup. You have this empirical risk minimizer here. Again, you take some samples and you look at the error in the worst case in expectation, and it's going to be the same rate as before with a small change that there's this little divided by gamma there. But this is actually fantastic because in this expression here, which is basically k divided by k plus d minus 1, the d minus 1 really is the main problem. Yeah, high dimension makes this thing a small exponent, and we want this to be a large exponent, because then m to the minus would be very small. So a large dimension would be a problem, and this gamma acts exactly on this dimension. So basically, if you increase the gamma, then you can get rid to some extent of the dimension dependence, which is pretty fantastic. You can also, in a sense, get rid of the dependence of k, because these will then just cancel. So if you have just a very large gamma, you will get very close to this rate m to the minus 1 that we want. Okay. We want to generalize this a little bit, because we don't only want to talk about smooth functions, smooth boundaries, but slightly more general stuff. And also, yeah, we want to introduce a new condition. And we also want to understand how optimal these results even are. So first, I'm introducing, well, there's still a little typo here. That's unfortunate. So this xx should be xd, and this d here should be an x. So somehow I mixed those two up. Sorry. So a horizon function is a function that basically is a function with a jump, and the jump is the graph of a lower dimensional function. Yeah. So here you see one example on the right. Basically, yeah, the jump curve is the graph of a function. And so now I can define piecewise smooth functions basically by saying that they're locally horizon functions. Yeah, so here I can look at a subset C of the continuous functions, and then I can say a new set omega has C regular decision boundary if, well, I can locally write it as a horizon function, and the function that describes this horizon function, that is in C. And to make it a little bit more flexible, I also allow myself to rotate this function with a p. Because otherwise it would always be a function in all but the last coordinates here with b, but if I allow also rotation, then basically everything is possible. I can have horizon functions going in all different directions. Okay, and I also need this covering entropy of the set. So we've seen it before already, but now I need to make it a bit more precise. So let's say we have a metric space X, and then we have an epsilon net, G epsilon, that is, so K is a subset of X. And we have an epsilon net in K if for every Y in this, for every K, X in this K, we have an element in G epsilon that is just not that far away. That is less than epsilon far away. And the size of the smallest epsilon net, that's going to be going to define the covering entropy of my set K by the logarithm. I take the logarithm of the smallest epsilon net, and that's going to be the covering entropy. Yeah, basically, I'm just trying to cover my set with a lot of balls of a certain size, size epsilon, and then count them and take the logarithm. Okay. And with this notion, we can now actually give an upper and lower bound on the best possible algorithm to learn these classification functions. I mean, this is a slightly special setup because we are looking at learning from completely noiseless samples. This is because we want to have a lower bound, and we say if you have no noise, it's going the lower bound would necessarily be the smallest because noise makes it harder. And it could be that if you just have a little bit of noise, you always fall into a different regime of complexity, so to speak, than if you say absolutely no noise. That's why we studied this completely noiseless thing. So if you look at the set of learning algorithms, AM, and so they take M samples and they go from the domain times sample set to the set of horizon functions. And then basically we have this expression. So let's go through this slowly. So let's start with what's in the middle. So I look at the best algorithm, A and AM, and then I look at the worst case performance. So I look at the supremum over all H in the horizon functions. And then in expected value, if I reconstruct or if I apply this algorithm to my samples, and subtract H, what is the L2 squared norm of this? And I can wedge this between two things. I can wedge this between m to the minus alpha over beta plus 1 and m to the minus beta over beta plus 1. But what are all these alphas and betas? Well, they only depend on the set C, the set that defined the decision boundary. And that basically through this, this formula here, I look at the L1 entropy of this set C. And this precisely defines how hard this learning problem is. Yeah, so here I want to reiterate that we're doing completely noiseless training, noiseless problem, because we want to have a lower bound that works for everything. Good. Proof is somewhat complicated because it's depending on this nice result by Barron and Young. But if you assume this, then it's actually not, the idea is not that hard. So basically we can just basically handcraft a certain set of densities. I'm going to call them PB. So for every horizon function HB, we can find an associated PB. And we can craft them in such a way that their squared Hellinger distance is basically related to the L2 norm distance of these HB1, HB2. Okay, so this is just a construction that we describe in the paper. But if you do this, then you can convince yourself quite easily that the L2 norm distance between HB1 and HB2, that's actually the same as the L1 norm distance of B1 and B2. Yeah, because if you have two sets, two horizon functions, basically one is here, one is here, and you're looking at, I mean, basically you drop them, kind of flip them in some sense, and then you look from the top. Yeah, so this is the area between those two functions that describes already precisely your L2 error, because that is where they don't agree, these two functions. Yeah, these are indicator functions of these sets. But of course, the area between two functions is just also the same as the L1 distance. Okay, so that's why we get this thing. And now you see why this whole thing is related to the L1 covering entropy of just the horizon functions. Okay. And then we can use this handcrafted set of densities that we have here and apply a pretty strong result by Baron and Young. Um, yeah, basically that will then give us upper and lower bounds of learning algorithms with respect to the Hellinger distance, but we can relate this to the L1 distance. Okay, what does this imply for what we've already done? Well, we know the L1 covering entropy of CK, and it's just epsilon to the minus K over D. And that would give us optimal learning rate in the no noise setting minus K over K plus D minus 1. And that's more or less exactly uh, what was established up to some log factors. What is of course not so nice about this is that that this suffers strongly from the curse of dimensionality. If you have a large dimension D, then this will not decay fast. Yeah, basically, you can divide everything by K and you have 1 over 1 plus D over K. So if D is much larger than K, well, you have a problem. And we also saw previously that you can get rid of the effect of D, but only by using a large margin. But then the margin exponent needs to scale essentially with the dimension. Okay, so this is what they have. Now we want to do it a little bit differently, and we want to also get some results, but without the curse of dimensionality. And there are just basically two ways that I know of that people use to attack curse of dimensionality in deep learning. And the first is this classical Baron space, and the other one is a slightly newer RBV2 space. So Baron space is just the set of functions f that have a bounded Fourier moment. I can define them slightly more generally, but this will suffice for now. So this is called gamma c now. And then there's also a second set, which is called this RBV2 space, which is quite natural in the set of in the context of neural networks. Basically, it's defined as all the functions f, where okay, you first take the Radon transform of your function f, and then you take a lot of derivatives. I mean, this is actually a specific differential operator in the radial direction, and then you look at somewhere at the total variation norm of this whole thing, and if this is finite, you're in the RBV space. And if you look at interpolation problems and you say your functions also need to minimize an RBV2 norm, then all the solutions will be real neural nets. So it's somewhat natural. Okay, and for these two sets, we have the following. If you have a function in the Baron space, f is in gamma c, then basically the L2 norm of an approximation problem, yeah, you take phi n being a neural net with n neurons, shallow neural net with n neurons. This error scales as c times n to the minus 1 over 2. Now that doesn't seem like an impressive rate because 1 over 2 is not good, but there's no dimension in there. So if it's a super large dimensional problem, well, then this is actually quite a good rate. And then the second result is the RBV2. Basically, it's a similar problem. You have f in RBV2. You want to approximate by phi n. Now you look at the L infinity norm. You could do the same in Baron as well. And you can show that the error decays like RBV2 norm of f. And then there's, again, the number of neurons, n, and the exponent is d plus 3 over 2d. So it's similar to 1/2. It's slightly faster. Okay. And now we have the following. Again, an approximation result first. Then I will talk about learning afterwards. If we have a function, a classifier function f, and it has a regular decision boundary, and in this case it's Baron, then we can find always a neural net with neurons. It always has 4 layers, so we don't need to do any scaling there. And for all measures, mu, we have the following expression. So we can upper bound the 0, 1 loss, so the measure of all the acts that are misclassified by our neural net, by the expression here on the right hand. So what you don't know yet about the right hand side is what C, K, and alpha are. And alpha is a parameter that depends on the measure. The same is true for C. So, and K kind of depends on this decision on the set B. Basically, we need to cover it in a specific sense. Okay, so this alpha, if the underlying measure has a bounded density, it's one. Yeah, so this rate is going to be n to the minus one half. But such a result could never hold with the 0, 1 loss if you have a different type of measure. Let's say you have a decision boundary somewhere, and basically your measure from which you're sampling is super concentrated along this decision boundary. I don't know why that should be. For example, it couldn't be if you have a margin, but let's assume that that's the case. Well, then you can almost not learn this, yeah, because every small error will just be amplified. So, but in that case, you get a smaller alpha here. So this alpha measures basically the concentration along the decision boundary. You can improve this rate if you have RBV2, but only slightly. But in total, this is actually not a bad approximation for a discontinuous function in high dimensions. So it's a discontinuous function. We are looking at the 0, 1 loss, yeah? So every mistake is immediately punished by counted as completely wrong. And we have high dimensionality. Yeah, so the dimension D could be very, very large. Still, we get this nice rate approximation-wise of n to the minus, let's say, 1/2. Do we have something similar with margin? Well, now things actually get quite interesting. So let's say we have more or less the same setting as before. Let's just, again say barren is the decision boundary. Again, we can find neural nets, 4 layers, and neurons. And assume now the measure mu has a margin condition with the C and gamma. Well, now this error that we're looking at, it scales actually as n to the minus gamma half. And that's kind of peculiar because, I mean, it's not super surprising because, of course, the margin condition is strong, but we are now approximating a discontinuous function in high dimensions with an arbitrarily good rate. Yeah, so gamma could be, I don't know, 10. So it could be n to the minus 5, which is a fast rate for a discontinuous high dimensional function. And there's no dimension in there. So with the margin, so before we were kind of limited to these approximation rates somewhere between 0 and 1, n to the minus alpha, and then alpha somewhere between 0 and 1, or even 0 and 1/2. But as soon as a margin comes into play, we can actually get fast rate. Okay. So from this, we can get a learning result. And I first want to state the one for, and I think I also need to speed up a little bit. First want to state the one for barren. So let's say we have a barren regular decision boundary. We choose our neural net in a smart way. I don't need to comment on this. So we know the number of neurons, we know the number of weights that we want to choose, and we have an upper bound on this number of on the size of the weights. We can learn in expectation with a rate that's m to the minus 1/3 plus a little kappa. Okay, but this kappa we can choose arbitrarily small. And if you replace barren by RBV2, then you have a slightly better rate. You don't have 1/3, but you have something like this. But for d equal to going to infinity, this will go to 1/3. With the margin, it's the same setup. Yeah, barren regular decision boundary, but now our measure also has this margin condition, and the learning rate is going to be this. So here you see in the exponent m to the minus gamma over gamma plus 2. Choose gamma large enough, you're getting very close to m to the minus 1. And that's, as I said before, the fastest rate we can achieve, but it's completely dimension independent. We don't even have to choose the margin depending on the dimension. There's simply no dimension left. We don't have to scale the margin with d to have dimension independence, and we get fast rates. And we get fast rates for the learning of discontinuous high dimensional functions. Okay, so yeah, so this is the optimal rate for all algorithms. Yeah, so we found it, for example, for gamma c, it was d plus 1 over 3 d minus 1. That's the optimal for all algorithms. But we can also show, we did show, that you could do the same thing with empirical risk minimization over neural nets. This is a specific algorithm, but it gets this optimal rate. So that's actually a good idea to train neural networks with empirical risk minimization here. We don't yet have a lower bound for the margin-based problem because our proof doesn't really work that well, because you cannot translate anymore these norms as soon as the underlying measures could have a margin. So then this translation of, I don't know, Hellinger distance of densities to L2 norm of horizon functions to L1 norm of boundary functions, it doesn't work that well anymore because we suddenly measure everything slightly differently. But the approximation problem is also interesting. I mentioned it before. We have a very high dimensional problem. It's discontinuous, and we work with the 0-1 loss, which is a tough loss. Okay, so we did a couple of experiments at least, but okay, they're of limited depth at this point. But this was to understand a little bit, does the smoothness of the boundary have that strong effect? And what we did here was we chose a class of functions. These are basically all sorts of combinations of sinusoids. And then we compute their norms, and then we normalize them with respect to different norms, and then we try and learn them. And we did it, in this case, only for quite low dimensional problems. D is 2, 3, and 4. And we first normalize with the soup norm. We normalize with the L1 norm. We do it with Barron. We do it with RBV and with C1. You can see in the pictures here what came out in the learning problem. So in the low dimensional problem, d equal to 2, yeah, you can even learn function classes quite well if you're only normalizing with the L1 or L infinity. But of course, it's better if the functions are in fact barren, and it's extremely good if the functions are in this RBV set, RBV2 set. So barren and C1 here are essentially the same. And that's also the case in 3D, but in 4D, we can already see them separate. Yeah, so barren actually becomes better in higher dimensions, which is exactly what, of course, we expect. RBV is always the best here. But what's also interesting is that you do need to have some regularity at the boundary, because if you choose L1 or L infinity, which do not actually introduce any smoothness as normalization, then you see already at dimension 3, you essentially do not learn anymore. And at dimension 4, these learning rates of the soup and L1 normalized function classes, they're just flat over all sets of, we take up to, I think, 200,000 training points, but we don't get any improvement because if the boundary is just not nice, then you just cannot learn them. So we need some regularity, and that is basically also my point. Why do we care about these regularities? Well, if you wouldn't assume them, then basically this shows you couldn't learn. So there is high regularity. We do also higher dimensional experiments, but now with margin. So here's an example where we just looked at basically learning the sphere is, or like 1/4 of a sphere is the boundary that we're trying to learn. And we build lots of data sets, and then we take different types of margins and try and see how well we can learn them. So this is a 50-dimensional problem. And you see here with different margin conditions. So gamma is 0, 1 at one point, so no margin, and gamma is 50, which is a lot of margin. And then here you can see how the errors scaled. They're nicely ordered according to the margin, which is kind of clear that this would happen. But also you see here in this high dimensional problem, no margin, so gamma is equal to 0, you're essentially not learning. Yes, so we went down to a little bit below 10 to the minus 1 as an error, which is pretty bad. But if oh, wait a second, I think this is, I think this is 0-1 loss, yeah, 0-1 loss. So, and then for large margin, you can learn quite well. Now you can go to almost 10 to the minus 4. And that's pretty nice. Okay, you might say this is all artificial data. we can also do something similar with MNIST. But our problem is, of course, with MNIST, we don't know either the decision boundary, nor do we know the margin condition. So what kind of experiment can we really do there? Well, we're producing. So we changed MNIST a little bit. So first of all, we train a sufficiently large neural net on MNIST, and then this thing defines our decision boundary, because then we can just say, where does it output 1/2? And this is basically where the decision boundary lies. And then using some kind of dataset augmentation, we can create all sorts of margin conditions that we want. Yeah? So here on the left, you see how MNIST usually looks like. We plotted it in such a way that we don't only separate zeros and ones. Red is basically this decision boundary that we got from our first initially trained neural net. And you see this has a massive margin. Now, if you want to reduce the margin, we need to fill this up. That's what we're doing with this augmentation trick. Basically, we're looking at all sorts of linear combinations of things from two classes. Okay, and then we get the following. Here, the effect is not that strong of the margin, but it is there. And in fact, I don't know if it's actually not that strong. So we didn't actually go to very high margin here. But basically, you have one margin parameter gamma equal to 0.1, and there you have as a learning rate. I mean, you're getting from a little bit over 10 to the minus 2 to just a little bit under 10 to the minus 3. So I'm saying this is roughly 1 order of magnitude, and the n is essentially 2 orders of magnitude. So it's a little bit faster than n to the minus 1/2. But if we have a larger margin, like gamma equal to 5, then we're going from a little bit under 10 to the minus 2 to a little bit under 10 to the minus 4. So we have 2 orders of magnitude. Yeah, for some reason, this is slightly better than it should be, because it's a little bit better than n to the minus 1. But this can also probably be explained. Now, so more margin definitely gives you better approximation, but we can already see that even with small margin, this decays quite nicely. So the underlying decision boundary is probably quite smooth. Good. Let's summarize. So classification in this traditional framework is a hard problem. And it's a particularly hard problem if you have a high dimension or have rough decision boundaries, or if you have high noise, or if you have no margin. But if you do have exactly the opposite, then it can be a nice problem. And in fact, it can be a good problem for neural nets because they get very close to the optimal thing. They get very close to the optimal approximation rates or learning rates even. One thing where this works, dimension independent, is if the boundaries are Baron or RBV functions. Of course, we don't know if they are in practice. There's no way to find out. But this is a model that at least allows learning. If you assume that the boundaries are CK, then in high dimension, that model would not allow learning. So this seems to be a sensible model because it is sort of agreeing with what one sees. Yeah, and we can all in all get close to fast learning rates, m to the minus 1, even if we have high dimensional, pretty rough functions. There are a couple of references here that I can come back to later. At this point, I think I should thank you for your attention.